Hello, everyone. Welcome to the VR&D webinar on Genesis structural optimization for ANSYS Mechanical, or GSAM for short. My name is Fani Aduri. I am a support engineer here at VR&D, and I'll be hosting this webinar. Today, our speaker is Dr. Hong Dong. Dr. Hong Dong is a senior research engineer at VR&D, and she has been working at Vanderbilt's R&D for about 7 years. She serves as the primary developer for the ANSYS interface to Genesis GSAM. Today she is going to speak about the features and capabilities of the new release, which is version 16. Before I pass on the mic to Ms. Dong, very briefly about VR&D. Our mission at VR&D is to provide the best optimization software that will enable designers and engineers to develop better products. And we try to do it with a relentless pursuit for excellence. We have two lines of products. One is the multidisciplinary line, which are design tools that can be coupled with any third-party solvers or softwares. And the other line is the structural analysis and optimization line, where we are trying to deal more specifically to structural problems. On the structural side of things, we have a few different software products, but our flagship product is the Genesis optimization. That is the optimizer or the optimization code that runs in the background with the ANSYS interface as well. We have 6 different types of optimizations. They are topology, sizing, shape, topometry, topography, and freeform. Ms. Dong, I believe, will go into a little bit more detail about it, so I'm going to skip those details in this introduction. Some of the other codes that we have on the structural analysis side, we have a fast eigensolver that is built into Genesis. So if you're using Genesis, you can use the fast eigensolver as well. It's called as SMS. We do provide it as a third-party interface too. So if you want to use it with other third-party commercial codes, you should be able to use it. Another one of our products is called ESL Dyna. It is an extension of the Genesis optimization capabilities to LS Dyna, which is a nonlinear analysis code. The advantage of using ESL Dyna versus other optimizers out there is the ability to solve very large-scale problems. Pretty much any optimization that you can do with Genesis, you should be able to do it with ESL Dyna coupled with LS Dyna. And it will give you a overall faster design process wherein the computational time is significantly much lesser compared to other tools out there. The Genesis integration with ANSYS Mechanical is what Ms. Dong is going to talk about in the webinar today. She's going to touch on both the different types of interfaces that we provide. One is a limited interface, which is limited to topology optimization. The other one is a structural interface where you can do all 6 types of optimizations that I was mentioning earlier. On the other side of things, in the multidisciplinary line, the flagship product is VisualDoc, which is a GUI-based tool to couple not just optimization, but other design process and integrate your design process with almost any analysis. The other tools that are there on the multidisciplinary side are optimizers, which we do provide to third parties as libraries that can be used. One thing I would like to mention here is we do have a coupling of VisualDoc with the ANSYS environment. So if you want to use VisualDoc along with your ANSYS analysis systems, you should be able to use it. Like I said, VisualDoc is a general purpose code. You not only can do optimization, but you can do other design studies like DOE, response surfaces, etc. And you can couple it with any third-party analysis. With that very brief introduction, I would like to pass on the mic to Ms. Dong, and she's going to talk about the GSAM-GTAM interface. Just before I pass it on, I would like to mention that there are free evaluations of all of our softwares that are available. You can go to our website and request for a free evaluation. Past webinars that we have done, the recordings are all available on our WebEx site. And the most important thing related to this webinar is if you have any questions for Ms. Dong, please use the Q&A panel in WebEx, and we'll try to address the questions at the end of Ms. Dong's presentation. So with that, I will make Ms. Dong the presenter and pass on the mic to her so that she can talk more about GSAM and GTAM.
Hi, good morning. My name is Hang Dong. In today's presentation, we will introduce the new features and the capabilities in the latest release of Genesis structural optimization for ANSYS Mechanical. This is the outline. We will first introduce the GSAM and GTAM workflow and some of the capabilities, and then we will talk in details about the new features in the latest release. So GTAM extension is the integrated extension that adds topology to the ANSYS environment. And the GSAM is a superset of GTAM. With the GSAM, you can perform topology as well as other optimizations such as topography, freeform, shape, sizing, and topography design. In the past 4 years, we have been working with ANSYS and some of our users to develop these 2 extensions. It started with the basic functionality, and now it is a more complete and comprehensive package. Here is the Genesis extension workflow inside ANSYS. So typically, the user will start with defining the analysis workflow, and then they can add the Genesis system to share the model information with other ANSYS analysis systems. And then user will go to the ANSYS Mechanical to do the pre-processing for the analysis. For example, they can, they define the meshing, define load and boundary conditions, and then they can move to the Genesis toolbar to define the design data. The design data include design region, objective, and constraints. With design region, the user will specify what's going to be designed or modified. And with objectives, they can define their goals, and with constraints, they will define the requirements that have to be satisfied. Once design data has been defined, the user click on Solve to solve the optimization problem. Then the Genesis will be launched in background. There will be some real feedback on the UI, for example, to view the design history plot, or you can check the printed log information in the solution output. Once optimization is finished, you can go to do the post-processing within ANSYS. You can check the, for example, topology, density, isosurface results, or you can check on the shape change results or other analysis results. As the last step, the user can export the optimized geometry as STL or edges file, then use the software like a SpaceClaim to clean up the geometry. Or the user can click on a button to update the ANSYS APDL input file with the design changes and run a quick validation with ANSYS. So this is the workflow of the Genesis extension. About the capabilities of Genesis extension, so Genesis can optimize for these analysis options. It can optimize for static structure, a modal, harmonic, random vibration, buckling, thermal, and nonlinear contact. And with the integration with the ANSYS solver, it can also optimize for the nonlinear static and the transient structure. Genesis can design multiple analysis systems simultaneously. For example, the user can design for static and model at the same time, or they can design thermal and structure at the same time. So it is supports the multiple analysis systems at the same time. About the optimization options, Genesis can do 6 type optimization. We will talk a little more detail in the following pages. So the first one is the topology optimization. Topology design is to find the best material distribution in a given design space. So typically, the user starts with a block of material, and the topology design will try to carve out the material and only keep the most important material. So at the end, the user will get a light and a strong structure. Here is the application of topology design from Pratt and Miller. They have used topology design to design the wing frame structure, the bracket of the support, the front and the rear and front upright, and also design for the chassis. So they have been able to reduce the weight about 65 pounds and also improve the torsional rigidity about 60%. For topography optimization, it is used to generate the bead patterns by moving the grids normal to the surface. So here you start with a flat plate, and the topography will try to move the grids up and down, and then create the bead patterns. This will make the flat plate stiff. These are some applications of topography optimization. Here it was used to increase the stiffness for the end hood panel, and this it is used to reduce the sound power of in oil pans. Freeform optimization is similar to the topography optimization. Topography is typically used for shell, and freeform are used for the solid structure. So So it can also generate the rip patterns by moving the grids along the given direction. In this example, it tried to move the grids on the top and the bottom surface, and then it generates this rip pattern. So by creating this rip pattern, it also makes the structure stiff, and the freeform can also use to reduce the strain or stress constitution. Sizing and topology optimization. Sizing is to design the dimensions of the elements, for example, the thickness of the shell. Here is to use sizing to design the thickness of these shells. Topology is a special type of sizing where every element is designed individually. Basically, if you look at the picture on the left, each shell has one color. That means it has one thickness. But on the right, the one shell can have different colors. That means it has different thickness distribution. So with topology, it can create some very interesting design. Here are some applications of using sizing and topology. On the left, sizing used to design the thickness of the car body and the rocket. On the right, topology design are used to do the reinforcement on the car. When we design products, we typically have some goals we want to achieve, and there are some design requirements that have to be satisfied. So these are the list of responses that can be defined as objectives or constraints. For example, you can define minimize mass as objective, or you can define minimize energy, try to make a stiff structure, or you can put some limits on the stress or strain. For model analysis, you can optimize for the frequency. For thermal, you can optimize for the temperature or heat transfer compliance. So, now we have given some brief introduction about the GSAM capabilities. Now we will go through the new features in the latest release. Here is the list of the key features in the release. So we have added some new fabrication constraints for topology, and we add the topology observation for thermal analysis, and also user can perform topology observation for the thermal mechanical coupled systems, and also add support for ANSYS using ANSYS eigenvalue solver, and support for the super elements and RSM. We will talk each feature in the following slides. So the first important feature we add is the new fabrication constraints, the new casting fabrication constraints with no-hole options. In the traditional casting fabrication constraints, it does not guarantee you don't get holes. So on the left, this is the traditional casting fabrication constraint result. You will get holes on the surface, on the body, and on the right, with the no-hole options, the topology will try to remove material from the top and bottom, and at the same time try to ensure a minimum thickness. So this, with this new casting fabrication constraints, it can give you a watertight design. So this is preferred in many design applications, such as that engine cover design and some other design that with a package. The second important feature we have added in the new release is the topology optimization for thermal analysis. Many users have been requested this feature. In the topology for thermal analysis, we added two new responses. One is temperature. The user can design to minimize temperature or put constraints on temperature. Another new response is the heat transfer compliance response. The heat transfer compliance is defined as the T transpose F, where the T is the temperature and F is the applied heat flux at that grid. So when HTC is minimized, the temperature at the grid where heat flux applied will be minimized. So by minimizing HTC, the user can maximize the heat conduction in a part. This is a very classic thermal topology opposition problem. So in this flat plate, there is a heat flow go into this entire surface, and on the top there is a fixed temperature applied. On the right, this is the temperature distribution. So for this problem, we want to minimize the heat transfer compliance, and we want to use 40% of the material. And the topology gives this tree-like structure that is the most efficient shape to dissipate heat. This is another example using topology with thermal analysis. In this condenser design, it has temperature, fixed temperature on the front and the back surface, and it has internal heat generation in the entire body. This is the temperature distribution. So in this example, we also want to minimize heat transfer compliance, therefore to maximize the heat conduction, and we want to use 20% of the material. So on the left is the topology result with no fabrication constraints. It gives a similar tree structure as in the previous example, but the user is looking for a more easy to design structure. So we apply the periodic fabrication constraints along all three XYZ directions, and we get this spin-like design, and the user is happy with the result. With topology, you can apply it to thermal analysis. You can also apply to the thermal mechanical coupled system. In this example, we have the steady state thermal, where it has convection in this three cylindrical surface, and it has temperature on the external surface. And we imported the temperature from the thermal analysis to static analysis, and this is the deformation of the structure. So in this example, we want to optimize for both thermal and mechanical structure at the same time. Basically, we want to minimize the maximum temperature in this inner cylindrical surface, and also we want to maximize energy to get a stiff structure. So we want to use 50% of material in this example, and here is the topology result. And you can see that topology created these members to make a stiff structure, and also make some holes which help dissipating the heat. Another important feature we add in this release is the use ANSYS eigenvalue solver to solve for modal, harmonic, or random vibration problems. The benefit of using ANSYS eigenvalue solver is that we can solve for some problem that Genesis does not support. For example, you can solve for cyclic modal analysis and optimize for the non-symmetric modes, and also you can optimize for the pre-stressed model. Here is the process of using ANSYS eigenvalue solver. Basically, we will call ANSYS eigenvalue solver to compute the eigenvalues and eigenvectors, and then transfer these eigenvalues and eigenvectors from ANSYS to Genesis, and use Genesis to do the optimization. At the end of one cycle, we will update the ANSYS model with the design changes, and this iteration will continue until convergence. So here is one example of cyclic modal symmetry, a cyclic symmetry with modal analysis. Basically, in this rotor split rotor brake design assembly. We use the cyclic symmetry to model this assembly. And start from index 13, it is the non-symmetric mode. And the user is interested in the harmonic index 1 and the mode 2, which is the index 14 in this table. So to use ANSYS eigenvalue solver, the user needs to add this external eigenvalue solver analysis setup node, and then specify use for that particular ANSYS analysis to use it with ANSYS solver. Here is one example. We use the same example. We are using freeform optimization to optimize for the non-symmetric mode. So we want to maximize the frequency for harmonic index 1 and mode 2, which is the mode 14 in Genesis. And we use the freeform optimization, try to perturb the external surface and to maximize the frequency. So here is the shape change result. It creates some ribs on the outer surface. And this is the design that is interpreted with the CAD software. With this external eigenvalue solver method used with ANSYS solver, you can also optimize for the pre-stressed model. In this example, the electrical motor, it has a pre-stressed condition which comes from the contact between inner and outer parts. So this pre-stress condition are applied onto the model analysis, and the user wants to maximize for the third and fourth frequency. And we here added some reinforcement. You see here the blue part, and we want to use 50% of this material and try to maximize the frequency. And here is the optimized result. With the request from one of our users, we have added the substructure support for the ANSYS super element. Basically, the substructure is a procedure that condenses a group of finite elements into one element represented as a matrix, and this matrix is called super element. So typically, the user can reduce the non-designable region as a super element. For example, the user wants to design the chassis in a big assembly. The part they want to design is the chassis, and all the other parts that are connected with the chassis can be reduced as super element. This will dramatically reduce the computation time, and also it allows solution of large problems with limited resources. So to use ANSYS super element in the Genesis extension, there are two cases. The first case is the part that is reduced as super element is still presented in the ANSYS mechanical model. For example, here this block is reduced as super element, but it's still presented in the entire model. So in this case, the user will need to export the DMIG file with a small script, like as is shown here. Basically, export the stiffness and mass matrices as DMIG file for Genesis. And then user will use the super element setup, this node, to specify which part has been reduced as super element. Another case is that the part that has been reduced as super element is not present in the ANSYS mechanical model. This typically happens when that model is reduced with mechanical APDL command outside of this model, and the user wants to bring in that super element into the ANSYS mechanical environment. So in this case, the user still needs to export the DMIG file, the stiff and mass matrix as the DMIG, and then the user needs to provide interface grid mapping file. Basically, for the grids on the interface, the user needs to specify what is the grid ID on that super element and the grid ID on the model. If the grids the locations are identical, they can just give the grid IDs. If it's different, the user needs to provide the coordinates and also the output coordinates system for the super element grid. So by doing this, the user can export the file and then provide the interface information for Genesis, and then Genesis will use these files in the optimization. Another feature we have added in this release is the standalone ESL for ANSYS. ESL for ANSYS is an implementation of the ESL method to perform optimization based on the ANSYS analysis. So with this integration, the user can optimize for nonlinear material, lattice formation, or transient structural analysis. Then we get this feature was implemented in the previous version. Then we get a request from user that they want to run this ESL for ANSYS through ANSYS RSM or on some supercomputer. So we developed this standalone case to enable users to be able to run through ANSYS RSM, and also be able to, if they want, they can export all the necessary files and run outside ANSYS Workbench. This supports both Windows and Linux. We also have been getting a request for support for ANSYS RSM. So now ANSYS Remote Style Manager is supported for both optimization with Genesis solver only, or optimization involves Genesis and ANSYS at the same time, such as the ESL or the external eigenvalue solver case. So to set up ANSYS Remote Style Manager, it requires setting up some environmental variable. For example, set up the path to the Genesis executable or the path to the ESL ANSYS installation location. And also, it require user to change a few lines in the mechanical ANSYS job list file, basically to specify what input file needs to be sent to the RSM server, and what output files need to be copied back from the to the RSM client. So these are the features we have been added that have been added to the new release. For the conclusion and summary, the Genesis extension is a user-friendly interface as an extension to the ANSYS platform, and it provides the high-end solution for multiple types of parameter-free optimization, such as topology, topography, topometry, etc. In this release, we have added many user-requested features, and it has been improved and will continue to improve the functionality for Genesis extension. This finishes my presentation. If you have any questions, you can ask.
Thank you, Hong, for the presentation. Again, if you have any questions, please use the Q&A panel in the WebEx window, and we'll be more than happy to answer. And while we are waiting for some questions, I do want to reiterate that we do have free evaluations for the software, and we have an evaluation form on our website. The link is up there on the slide. If you have any questions after the webinar, there are a couple of support email addresses that are also shown there on the slide. You can send us an email to those email addresses. One thing, we will provide a recording for the webinar in about couple days time. Once the recording is ready, we will send you emails on how to access that recording. Okay. Hong, one question. During the optimization, is it possible to define displacements as a constraint? That was one of the questions that came in.
Okay. Yes, the user can define the displacement as constraint.
Okay. What Hong showed in those examples are just a few examples. There is a whole big list of responses that you can use either as objectives or constraints. And they are available in the interface. Moving on to the next question is, or along those same lines, a follow-up question is, can you increase the deformation or increase the displacement? So I believe it's no longer a constraint. I think it would be an objective, whether you can increase the displacement or not just decrease it.
Yes, the user can, for example, in that compliant mechanism, is actually try to maximize the, way to maximize the deformation. It's not directly use deformation as constraint or objective, but it's using a different formulation, which in result will maximize the deformation at some location.
Yeah, just to clarify on those lines, yes, you can put in an objective to increase the deformation or put in a constraint that is more than the actual value that you have at the baseline, so that it would actually try to, it can have the freedom to try to increase the deformation. Okay, moving on. Does Genesis support the frictional contact defined in ANSYS Mechanical?
Yes,
and along those same lines, what are the nonlinearities that Genesis supports?
Genesis itself supports the nonlinear contact, which includes frictional or frictionless contact. If you talk about other nonlinearities, if you use the ESL with ANSYS, it can solve for the large deformation and the nonlinear material.
Okay. All right. Another question, Hong, is again the usage of a response for either an objective or a constraint. Can you use stress as either as an objective or a constraint in the case of structural optimization?
Yes. stress can be used as objective or can be used as conference. Yeah, the response is that in the response list, in this list, they can either be used as objective or as conference.
Okay. All right. Okay. Going back to increasing the deformation, do you have any example? Do you in the presentation?
We have the compliance mechanism, that example, in the manual. We can provide that to you after the seminar.
Mm-hmm. Yeah, if you have the extension installed, even if it's an evaluation copy, the manual is there along with the installation. If not, please contact us, and we'll be more than happy to provide you that example. Okay. Switching to the stress as an objective or a constraint. When you define stress as objective or constraint, how does Genesis take care of areas of stress concentration? Do you have to do something about it, or how do you define it?
About the stress concentration, do you mean that artificial stress or the true stress?
Artificial, yeah. Say near a notch or something like that. I can answer it if you
Okay.
Essentially, when you define a stress constraint or stress as an objective, you are specifying the areas or the elements where you want to use the stresses for. And if you know that there is a stress concentration in a certain area, you just leave it out from the specification of the stress responses. So, in other words, you leave out the elements where you know that there is stress concentration, and only use the elements that that you are interested in. Okay. All right. I guess that's it. Again, I would like to thank each and every one of you for your time taken in attending our webinar. Again, I will remind you that you can request for an evaluation. We provide full feature evaluation licenses so that you can test out the software. And if you don't have any more questions, please send us an email at gsam.support@vrand.com or just support@vrand.com, and we'll be more than happy to answer. Thanks a lot. Good evening, good night, good afternoon, wherever you are, and have a good day.